Melanoma is one of the most deadliest forms of cancer. This disease is a problem that affects a good part of the global population, regardless of age. As with many cancers, the severity of the disease worsens as time without treatment increases. As a result, being able to identify the disease early gives patients more time to fight the disease, which in turn increases their chance of survival. However, the healthcare industry lacks the personnel to be able to look at every potential case in detail. Cleverly designed neural networks could be used to make up for this. UNet is one of the most popular CNN architectures when it comes to semantic segmentation. This is likely due to its good performance and the fact that it works even with limited datasets. However, corporations such as Google have been developing their own robust architectures to compete with UNet. So our group wanted to experiment with neural net architectures and see if we can come up with a model that improves upon the standard UNet architecture. As you'll see later, each of my group mates took vastly different approaches to this problem. The approach I took was to explore how modern neural net architectures such as Google's Deep Lab fare against UNet, which is evident in my research question. The dataset we used was provided by the International Skin Imaging Collaboration, who assembled it for the 2017 challenge. Before talking about the models I developed, I will talk about the data manipulation techniques that we used to improve our model's performance. Note that these techniques don't involve any machine learning or neural networks at all. First, let us talk about the pre-processing. Every image was resized to 256 by 256 due to memory limitations. After that, each image's contrast was increased by normalizing it, then performing gamma correction on it, then applying the contrast-limited adaptive histogram equalization on it. Finally, we used a technique called simple linear iterative clustering, SLIC, which uses k-means clustering to generate a superpixel representation of each image. We used the skimage library to do all of this. Next, let us examine the post-processing techniques that we used. First, a series of opening and closing operations is performed on the image to get rid of gaps and isolated blobs. We performed the aforementioned operations using kernel sizes of 3, 5, 7, and 9. After that, we identify all of the contours in a given image, find the biggest one, and discard the rest. We do this because our lesion is almost always one contiguous region, and is more often than not the largest one. We use the OpenCV library to do all of this post-processing. Throughout this project, I was able to develop two vastly different models using Keras. The first model I developed, which we presented in our progress report, is UNet. The model outlined in the diagram above is a fairly standard implementation of the UNet architecture. This next model was inspired by Google's Deep Lab. Instead of using modified aligned exception blocks, we used resnext blocks with a cardinality of 16 for feature extraction. Both DeepLab and resnext are known to perform well in computer vision tasks separately, so I combined the two in the hopes of developing a better model than UNet. Moreover, I noticed that older versions of DeepLab use ResNet blocks, so I wanted to see how well its successor fits with DeepLab. We also used dilation rates of 1, 2, 4, and 8 in our implementation of DeepLab's Atrius Spatial Pyramid Pooling, ASPP, rather than using multiples of 6. This decision was made to accommodate smaller image resolutions and limited memory. Here are the training parameters I used to train both models. In this next part, I will discuss the process that I used to transform the raw probabilities outputted by the TensorFlow models into prediction masks. As can be seen in the diagram, we used two instances of our model to generate predictions. One of them was trained on the pre-processed dataset, and the other was trained on raw images. We found that both instances perform relatively well, but get caught up on different things. So to balance out those issues that they had separately, we take both of them into consideration. Both instances use a threshold of 0.5 to assign labels. A conditional random field was also used to make inferences based on the calculated probabilities. If this CRF, or either of the two aforementioned model instances, label a pixel 1, then the final output will label said pixel 1. I chose to do all of this since the models tend to be a bit more conservative than the ground truth. And here is how each model performed on the test set. As can be seen in figure 6, the DeepLab plus ResNext model has a much lower average loss, regardless of the post-processing used. Moreover, while we see that binary accuracy remains relatively the same whether we use post-processing or not, both models improve in terms of the IOU accuracy when post-processing is used. We can also see from Figure 7 that our DeepLab ResNext model outperforms the UNet in both measures. The main takeaways from this are as follows. UNet seems to be outperformed by newer, more robust architectures such as the one developed in this project. The next step would be to improve our model using more sophisticated pre-processing techniques such as hair removal and more complex mask generation algorithms such as max flow approaches. Finally, here are the resources that I used to make this poster. Thank you for listening.